more easily solvable. And maybe I can write this as I equals to delta t A conjugate transpose B dot A, and then plus K Lk dot A minus E sub K conjugate transpose dot with L K dot A minus E sub K. Okay, you can write that equation as such. And then I can take the variation in order to minimize it. I take delta I. Okay, delta I with respect to the change in A. I let A be equal to the optimal value plus delta A. If I substitute that into the above, I get delta I with delta T, delta A, conjugate transpose B, A naught, and then I take the first variation of this one, I get A naught, conjugate transpose dot B, dot delta A. So that is the variation of the first term. If I take the variation of the second term, I will get Lk dot delta A, and then this is a constant. When you take variation, it becomes 0, and then Lk dot A naught minus Ek. And then there should be a second term coming out, because I have to now take the variation of this term. So it should be Lk dot A naught minus Ek, taking the variation of the second term. Okay. And this one to be 0. If I have struck the optimum value, if A naught is the optimum value, this first variation should all be 0. Okay, this first variation should all be 0. I can see that it would be 0 if this is true. I can write this as the transpose. Okay, this is delta A conjugate transpose dot Lk dot A naught minus Ek. I can write this as such. I can do the same thing to the other one. But if I collect all terms with delta A, okay, delta A, they must cancel each other. So this term must cancel this term over here. So I have the fact that delta T be A naught plus Lk conjugate transpose dot Lk dot A naught minus Ek must be equal to 0. Okay? And if I take the term that has delta A alone, they must also cancel each other. But the equation that you obtain is exactly the same as this equation. There should be a conjugate transpose. Okay? So I can take either matching the delta A conjugate transpose term and get this equation, or matching this with that. If I match this with that, I get exactly the conjugate transpose of this equation. So I don't need to write it 2 times. So if this equation is satisfied, that equation above would be 0. And then if you look at this equation, you can write it in terms of Lk conjugate transpose Lk plus delta T B dot A0 must be equal to Lk conjugate transpose Ek. So this is the equation to solve for your unknown A naught. And this problem now is made well false. Before that, it cannot be inverted. Because if you have had make delta T equal to 0 and not put in the optimization of the norm term, then this term will have disappeared. This term will have disappeared. And then if this term is not there, this matrix system cannot be inverted. Okay, you find that this matrix system has a lot of zero eigenvalues. And because it has a lot of zero eigenvalues, you can never invert this matrix system. Are there any questions so far? Yes, Aditya?
If you can't invert a matrix system, it means it's low rank, right? Which means why can't you use numerical techniques to...
Oh, you can do singular value decomposition too. That's what people do. This system, without the optimization term, I put in this term here in the functional so that that term emerges. If delta t had been 0, okay? B is a Hermitian positive definite matrix. You can prove that quite easily. So this would only have positive eigenvalues. This one, however, if you naively set up this problem and try to solve this equation, you'll be doomed to disappointment. You find that this has no inverse. Even before you do that, even if you try to solve this equation, sorry, this should be A naught here. Even if you try to solve this equation, you'll be doomed to disappointment because this has no inverse. Then the question to ask, why are these problems giving rise to matrix systems that are opposed or non-invertible? There is a physical reason for it. This is the inverse scattering problem. We measure the scatter field away from the object, and we try to construct the object function O. So we try to construct this function O by measuring the data away from it. That itself is a very opposed problem. The question is, do you understand why it is opposed? That is, you're trying to infer what the object is from the scattered field away from the object. Okay? So the inverse scattering problem is always opposed. There's no unique solution. I can quote you a very simple example. Right? Because we are doing inverse scattering every day in our life. I look at you, I'm doing inverse scattering because I don't mean that. I don't supposed to. Yeah, okay. I thought it's maybe motion sensitive. So I'm doing inverse scattering every day in my life when I look at you with my lens. Is the image that I observe unique? It's not, right? It's not that you look different every day, but you're not unique. Why? Because I cannot count the number of hair you have on your head with my inverse scattering technique. My inverse scattering technique I have is band limited, the slow pass filter. So I can see you, but I do not know you exactly. I cannot count all the hair on your head, right? And cannot count all your pimples you have on your face, right? So inverse scattering by itself is not unique. So if I have a scatterer, if I try to construct this scatterer, if I add some small features to it and perform the same experiment around this scatterer, I'm not going to detect these small features, especially if the small features are sub-wavelength. If the small features are sub-wavelength, even actually your hair is not an example of sub-wavelength features. I cannot reconstruct your hair because of the limited resolution of my eyes, because I only have so much Fourier data. Okay, so inverse scattering problem is entirely non-unique, also due to the fact that if you have anything that is sub-wavelength, any corrugations you add on the surface, if you shine light on this, what kind of reflected wave do you get? Yes?
You get multiple scattering.
You get multiple scattering. Say, let me go through a simple thought experiment with you. Very simple. The Duncan experiment. Okay? So, I have a flat surface. I shine in light. I get a reflected light. And let me assume that this surface has been roughened now, but roughened to a length scale that is much smaller than wavelength. Okay? So I roughen So this roughness is much smaller than the wavelength. How is the scattered field affected by this roughening of the surface? Yes? Have you all studied flocate mode theory? If I cast this into a solvable problem, we will make this into a periodic structural problem. Make it solvable by the flocate mode theorem. Then there will be the zeroth order mode, which is a specular reflection. There will be higher order modes. And what happens to the higher order modes in flocate mode theory? Ken, do you remember? No? Does anybody remember your flocate mode theory? We talked about block wave a little bit in this course.
Are they alias back to?
No, they're not alias back. They are evanescent. Okay, they're cut off. Okay, if you look at the flocate mode theorem, you expand the field in terms of the dominant wave plus the high order modes. I can, maybe it's 2n Ix over L. This is flocate mode theorem. You expand it in terms of the dominant wave plus the high order modes. And if this period is very small, it means L is very small. If L is very small, then Kz, which is this direction, is given by K naught squared minus Kx squared. Right? Kx squared is this in total. So it is this plus 2n pi over L squared. And what is Kz? If L is very small, Kz is evanescent. So the first thing that you observe when you roughen a surface at a very small length scale, much less than the wavelength, you can roughly understand it with flocate mode theorem. You only produce evanescent waves as a scattered wave. Okay, which means that if you roughen a certain thing at a length scale much smaller than wavelength, it will not affect the far field. It will only affect the near field, because whatever happens here is just evanescent wave. And this is very much a part of nature, that you can make small changes to a scatterer. It's not been felt or realized at the receiver points. And hence, you can make small changes here, and it's not felt at the receiver point. What does that mean? This has a null space. This inherently has a null space. So this problem is not solvable, neither is this problem. Okay? Neither is this problem. But this problem is solvable. Okay? So maybe you can take a coffee break, but before I take a coffee break, do you want me to tell you a number of jokes? Okay, I have a number of jokes I can share with you. One is about, I told you about a musician, a professor, and a graduate student, right? And then there was another one about a professor, a postdoc, and a graduate student. And they went out to lunch, and in the park they met a genie. You know what a genie is, right? She's very powerful. She can grant you anything that you wish. So the graduate student, the genie told the graduate student, I can grant you a wish. What do you want? The graduate student say, oh, I want to go to Hawaii. You know, beautiful people on the beaches there can just relax. So the genie granted him the wish. And then the postdoc asked, you know, the genie asked the postdoc, what do you want? The postdoc said, oh, I want to go to the Bahamas. Nice beaches, you know, beautiful people, and so on. So the genie granted the postdoc a wish, and off he went to the Bahamas. Then the professor, then the genie asked the professor, what do you want? The professor said, I want both of them back in the office after lunch. So we take a coffee break.